Word association. Let's see if we remember this game of word association. At the beginning of the word, atom, 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 and neutral means, right? Now we drew our cat on Friday, and we said it was called a cat ion. So here's our next game of word association. If atom goes with neutral, ion goes with charge. So let's try it. Ion. Charge. Ion. Charge. Ion. Charge. If neutral means electrons equals protons, what does charged mean?
Electrons does not equal protons.
And we started our explanation for why that would happen on Friday, right? Why we would have it so we would gain or lose electrons. Now here's what I'm going to tell you. Always, if we gain or lose something, it's always the number of electrons that changes. It's never the number of protons that's going to change when we form an ion. Think about it this way. If the protons and neutrons are tucked ever so safely away in the nucleus, and the electrons are the thing on the outside, it is much more likely you lose something that's on the outside, right? We can think of several silly examples. How many of you have traveled overseas before? How many of you, when you traveled overseas, were advised to get one of those passport holders? Never had to do it? When I was your age, I took one of those trips overseas with the high school, and my high school English teacher made us buy one of those straps that goes across your body that you tuck your passport into that you wear underneath your clothes. You can imagine how comfortable that was. But the reason for it, where did she not want our passports?
From the outside, in a pocket, you think?
Yeah, like got a pocket on the outside. Why? Yeah, you put a whole bunch of American kids walking through Covent Garden in London. Pickpockets are looking at us like we've got giant signs on us that say easy mark. Because we did. So where is the stuff that's safest? Closest to the center. So the stuff that's never going to change in an atom will be the stuff that's closest to the center to make an ion. Never going to change protons. We only lose the stuff on the outside. And in the instance of ions, we only lose the electrons on the very outside. Do those electrons have a name?
The outer shell.
They're the outer shell, also known as valence electron. Is there a trick for knowing how many valence electrons something has? If you have like a super secret prop that you could get out and show me, like a cheat sheet, if you will. A cheat sheet you'll be guaranteed to use on every chemistry test you ever take. Ooh, what is our cheat sheet?
Periodic table.
How do we use our cheat sheets to tell us how many valence electrons an atom has?
If the American system uses 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So then that's the amount of valence electrons.
So that's the number of valence electrons. And what number are we aiming for? What is energetically favorable? 8. 8. It's called the complete what?
Wait.
Having 8.
They're the lower gases.
They'd be a noble gas configuration. They'd be just like the noble gases. It's a complete octet. So our goal is to complete an octet. Now let's make sure, should we start with a cation or an anion? What is it? Cation? Just so we can draw the cat again? What charge does a cation have? Is there something that gives it away? They are positively charged ions. Looking at that periodic table that's in front of you, can you pick something, anything, any column on there? Which columns do you think are more likely to become cations, or more likely to become positive? Robbie. 1 and 2. How about 3? Yeah, so 1, 2, and 3 are more likely to become cations. In fact, metals. If you look at the periodic table, metals are going to become cations. So, let's see. Can you pick somebody from column 1 for me?
Hydrogen.
Can we pick somebody who's a metal in column 1?
Potassium.
Potassium. Okay. Okay. Potassium, the atom. How many protons does it have? The atom. Chad?
19.
How many protons will the ion have?
19.
How many electrons does the atom have?
19.
Why do I know that sound? Thank you. Now we know because it has 1 valence electron. It has 1 valence electron. Is it going to gain 7 more electrons or give away 1? What's easiest?
Give away 1.
Give away 1. So if it gives away an electron, how many electrons will it have? 18 total, 8 in its valence shell. Because remember, think about our bookshelves that we talked about on Friday. If you take one off that top bookshelf, we then have our full bookshelf just below it. So that's what we do here. We denote the difference between atoms and ions. Here's the symbol for our atom. Here's the symbol for the ion. So we just say what charge it has. It's a +1. So now instead of calling it just potassium, we're going to call it potassium ion. Okay with that? Potassium is now very happy. Has a complete valence shell, has a slightly positive charge. Actually, it has a positive charge overall, +1. What would column 2 have for a charge?
2.
+2. And column 3? Column 1 is a +1, column 2 is a +2.
+3.
+3. Okay. If metals make cations that are positive, we're going to go to the opposite side of the table to do the opposite, right? So let's pick somebody from the opposite side of the table. Are we going to take anybody from column 8? Why not?
The only full shell.
It's the only full shell. Why would they lose anything? They're already happy. They're noble gases. And remember, we already said some pretty strong things about how nobility really does nothing. So pick somebody from a column that does something. A column that actually does something.
7.
Okay. Who in column 7 should we pick on?
Bromine.
Bromine. I should tell you these are columns, let's see, 5 through 7. And they're going to be negative. And this is our nonmetals. All right, bromine as an atom. How many protons?
35.
How many electrons as an atom? As an ion, how many protons?
35.
Now it's in column 7, which means it has 7 valence electrons. If it has 7 and it wants to get to 8, is it going to get rid of 7 or gain 1? If it gains an electron, what should I do to the total number of electrons here? The symbol is bromine for the atom and Br minus 1 for the ion. Now, unlike potassium, where we just said potassium and potassium ion, those are their names, something weird happens to the anions. Instead of calling them their names and just adding the word ion, we change the ending of the name to IDE. So instead of being bromine ion, we're going to call it bromide. But you knew that already. If you've ever said the word fluoride, right? Stuff the dentist puts on your teeth. Or chloride, that's just telling us it's the ion of those atoms. Do you think you've encountered the ions of these atoms more often or the neutral version?
Ions.
Why would you encounter the ions more often?
Because they're more safe, because the other ones want to get that last electron violently.
Everybody's going to react to get that last electron, right? So if the point is to react to get your electron, you're going to do that. So most of the time when we encounter all of these things from the periodic table, they're participating in some kind of reaction. For instance, it's going to be what we call bonding. And for you guys, this first kind of bonding is going to be pretty obvious because we just did something with potassium. What charge did potassium ion have?
Potassium had a positive.
A positive.
Or positive 1.
Positive 1. And what charge did bromide have? Negative 1. What do you suppose that does to potassium ion and bromide? It makes it neutral if they do what? If they bond, if they stick together, right? They're attracted to each other. So the first kind of bonding we're going to talk about is with these ions. And it's ionic bonding. Here we're going to have a transfer of electrons to complete the octet. So both participants in this bond will have a complete octet. They will both be happy. They'll transfer the number that they need to complete their octet. Sometimes it's 1, sometimes it's 2, sometimes it's 3. Depends who's participating. And the resulting particle is called a salt. Now this is tough because you guys hear the word salt and you automatically think of what? Sodium chloride, right? Table salt. Table salt is one kind of so many salts, I couldn't even tell you how many kinds there are. But it's the same reason that you don't eat road salt. Road salt is not just large chunks of sodium chloride. It's a different set of ions that have bonded together. But we call them salt because they're ionically bonded. So don't be confused by that word. We see salt and we automatically, or we hear salt and we automatically think table salt. Not the same thing.
What bonds make road salt?
It would be calcium chloride most typically, and sometimes potassium chloride. But either way, you don't want to season your food with road salt. Not edible. That's good. This is usually that moment that I have a student say, I did that once in kindergarten. And we're just like,
What would it do to your body if you did that?
oh, you'll vomit. I mean, if you're okay vomiting, that's cool. Anybody okay vomiting? It's unpleasant in general. Dehydration, vomiting, imbalance of particular ions that you have dissolved in your blood. Vomiting is typically your body's first response to get something out that could do much more damage. Any ionic bond is going to be between one metal and one nonmetal. So it will have one cation and one anion. When they bond together, when the positive and the negative are attracted to each other, the overall particle, the resulting salt, is neutral. But only after the bond has formed. Before the bond has formed, it's not neutral because they're charged, right? Positive or negative. How do we feel about ionic bonds? We get why we would transfer electrons? Like, yeah, okay. If they want 8, give them away, keep them. Let's see. Calcium, when you tell me the size of the charge, the magnitude and the charge itself, is going to be a superscript, super like Superman, it's in the air, it's up above. When we make the compound, it's going to turn into a subscript down below, like a submarine. Super like Superman, sub like submarine. Super, sub, super, sub. Sometimes you get those confused. So, how about fluorine? Our friend fluorine, when it turns into fluoride, what do you think? What symbol should I use? James?
F minus 1, because it's a negatively charged ion by 1.
It is indeed. Now, I told you guys that these are going to bond together to make something neutral, right? How many fluorines will it take to make calcium neutral?
2.
It's going to take 2. Why is it going to take 2? Why will it take 2? Discuss it with your group for a moment. Talk about it.
Because 2 minus 1 is 11. You add
Calcium's got to give away 2. That's what you said, right? Calcium has 2, and it's like, hey, I have 2 I need to get rid of. But fluorine's like, I only need 1. I don't want your other one. Don't give it to me. What if a second fluorine shows up?
Then calcium can give it to the other fluorine.
Yeah, calcium can give it to the other fluorine. The other one's like, hey, yeah, sure, I'll take that. So we end up overall with a compound that looks like this. Calcium fluoride, CaF2. This is where our subscript comes in. I want to make sure we know the difference. Superman, superscript, subscript. That's how ionic bonds work. Did you notice something about this ionic bond thing, though? About what we do with our electrons? Key verb in the definition for ionic bonding. The what of electrons? The what?
Transfer.
Ionic bonds are all about giving or taking electrons. Give or take. Is there another option?
Do you share?
What? share. Do ionic things share ever? No. Ionic things do not share. Now this is what saddens me greatly. I say the word share and I think of the Care Bears because that was my generation, like old school Care Bears with like the Care Bear stare. And I fear you guys have no idea what Care Bears are.
Yes, I do.
Oh, that's good. And I feel like I can adequately do the Care Bear stare now. Like, yeah, they all line up, they're like, I can totally do that now. Oh, I want to be Funshine Bear. Funshine? Good choice. You don't know what I'm talking about?
There's a rainbow one.
Funshine, right?
That was? I think that was the yellow one.
With a sun.
Yeah, and then there was a blue one with a rainbow.
Wasn't it like a sad one?
Grumpy?
Grumpy. Yeah.
Nobody wants me to be the blue one with the rain cloud.
Oh, that's what it was. Yeah, there was
So, what you're telling me is there's another option. I don't have to go Santa Claus or Grinch, but I can go Care Bear. We're talking about sharing. We're talking about sharing. It's the only way I can remember it. The other option for us then is not Santa or Grinch. Ionic bonding is Santa or Grinch. Those are our choices, positive or negative. But instead of doing that, we can accomplish the exact same thing by sharing electrons. And sharing is caring, and everybody knows that, right? So we can share electrons. But I must tell you, there's one group of elements that they just don't share.
Nobility.
Well, they also don't share. Definitely don't share. So our noble gases are still not going to participate in this. But Santa Claus never offers to come to your house to share your Christmas gifts with you, right? Like he just drops them off and he leaves. Metals are always going to behave like Santa. Metals are always going to just say, take these electrons, I don't want them. So the only atoms that are ever going to participate in this kind of bond, where we share electrons to complete an octet, only ones who will ever do that are going to be nonmetals. And this actually works out pretty well because if we think about the story of the Grinch, if we think about his conversion at the end, like, yeah, he was a taker, but at the end, he didn't take Christmas from the Who's. He shared it with them, right? He stayed at the Christmas dinner table. So if we think Grinch post-conversion, he's willing to share. So any nonmetals are going to share electrons. Now here's what I want you to do on your whiteboards with your partners. Yep. Identify which columns by their number in the American system, which columns you think are going to share electrons, and how many electrons do you predict or hypothesize that they will share? How many electrons do you hypothesize they'll share? It means I can just like go home, right? Yeah? You don't need me. I'll just go home. You heard that, right? They said they can learn perfectly capably. I see a lot of, let's see. Ooh, I see a lot of column 7. How many of you agree column 7 is going to be willing to share electrons? How many electrons will column 7 be willing to share? How many of you wrote column 6? How many electrons will it be willing to share? 2. And column 5, how many of you wrote 5? How many will it be willing to share? 3. And column 4? 4. Colin? 4. All you have to do is take the American column number and figure out exactly how many it takes to get to 8. That'll tell you how many electrons it's willing to share.
What about 3? Because it has 1 in there and also 1.
So here's what's a little bit tricky. Hydrogen, our friend hydrogen, remember how we said, oh, hydrogen violates all the rules. Hydrogen is in fact going to share. Hydrogen will share only 1 electron. I know, you're like, but it has 1 electron. It's going to be willing to share 1. That means its complete octet has 2. Yes, it wants to be just like helium. So it violates the rules. So hydrogen is in fact going to share 1 electron. It will be the only member of column 1 who will do so. When we look at the other columns, if you colored them as a nonmetal, the nonmetals will be a sharer. If you colored them as a metal, they will not share. Can you think of, on your whiteboards, make a list of compounds you think share electrons. So any compounds that you think share electrons. Covalent compound. And we know that this compound is covalent. It's a single molecule. That's the word we use when we share. When we share electrons, we use the word molecule. My favorite molecule, and I know it's a molecule because it contains hydrogen, who is a nonmetal, and oxygen, who is a nonmetal. Agreed? Yep. Both nonmetals, that tells me that they're sharing. Now, most of you have probably seen something that looks like Mickey Mouse. And then you put an O here, and H is in his ears, and there's our friend water. And then I draw on the bonds itself, then it goes from looking like Mickey Mouse to an angry koala. So we see the angry koala? Each one of these lines that I drew on as angry koala eyeballs represents 2 shared electrons. I told you that hydrogen's willing to share how many electrons? 1. And oxygen is willing to share how many? It's in column 6. 2. Well, look, here's oxygen. It's sharing 1, 2. And here's hydrogen sharing 1, 2. If oxygen is sharing 2 electrons, its octet is now complete. And if hydrogen is sharing 1 electron, its octet is now complete. So this bond forms just to complete octets. All it is to complete an octet. Has it done so? Yes. It's happy. It's made a molecule, and it's sharing. I won't